Okay. Hello, everybody. Good evening. A very warm good evening, good morning, and good afternoon to everyone watching the event today from across the world. So we've had more than 250 registrations from. Hello, everybody. Good evening. Very warm good evening, good morning, and good afternoon to everyone watching the event today from across the world. So we've had more than 250. Yeah, sorry. So yeah, so we have about more than 250 delegates watching this event from around the world, especially from across US, Europe, and India, as well as Middle East. And amongst this 250 are our partners and a whole lot of our existing customers, and special welcome to all of them as well. So before we start off the program for the evening, I would just like to take a couple of minutes to run down the memory lane and see how we got here, right? So it was in 2017, end of 2017 or 2018, that we launched our first product, BalanceEye Video Oculography System, which has now become a household name in the vestibular assessment space. We have more than 370 clinics and hospitals using this product, and more than 200,000 tests have been performed on the platform. It's probably the largest installed balance assessment platform in India as of today. So very recently, in last year, we got CE certification as a Class 2A medical device for BalanceEye Video Oculography System. And this opened up large markets for the product as well. So as we speak today, BalanceEye VOG is installed in 11 countries around the world, and the tribe is growing pretty fast. So with this vast experience of having built and launched the product successfully, right? Today, we bring to you our next product in the portfolio, BalanceEye DVA. So it's primarily a solution for dynamic visual assessment, dynamic visual acuity assessment. So it's a very small, compatible, very small portable product. You will see when we do a detailed show and demo of the product. And it's got a whole lot of capabilities built into it, starting from assessing vestibular ocular reflex in all semicircular canals, to unmasking deficits in concussive head injuries, to monitoring progress of rehabilitation of vestibular deficits. It can do a whole lot of things. It can actually add tremendous value to a vestibular lab, and it comes in a very, very small form factor. So this is the product that we are going to be launching today. But before we move on to the launch, let me just quickly run through the day's agenda. To start the evening, we have a 45-minute lecture from Dr. Srinivas, who's the co-founder and heads product innovation at Cyclops MedTech. And he's going to talk about dynamic visual acuity as a science and its clinical significance. And post the lecture, Dr. Deepak Aldepur, who is a senior ENT consultant and director at Trustwell Hospitals, and also the past president of AOI, is going to be unboxing the product. Post which we have lined up a quick demonstration of the product and a couple of case presentations. And towards the end, Dr. Ravi Nair is going to wrap up the event. And if you have any questions, please do put the questions in the chat box on the YouTube live stream. We have someone moderating that stream, and after the product demo, we will be answering a few of those questions. So with this, I would now like to invite Dr. Srinivas to start the session on dynamic visual acuity and its clinical significance. So over to Dr. Srinivas.
A very warm good evening to all of you, and I'm really thankful for all of you for joining from the depth of my heart. It's a great privilege that you're listening to this and you've taken the time out to be with us in this special occasion. So I'll now be talking about dynamic visual acuity and its clinical significance. Okay, what are the prerequisites for clear and stable vision is the thing that we need to answer first. Okay, so when you look at the diagram longitudinal section of the eye, okay, so here is the on the back part is the retina on which the image actually forms of the world, and there is one particular area all of us know that is the fovea, and fovea is the area of the sharpest vision. How important is that fovea is that image of the object of regard, whatever we are looking, should be brought close to the center of this fovea. The best spatial resolution is within 0.5 degrees from the center of the fovea. As the image moves 2 degrees from the center, the visual acuity actually reduces by 50%. So that important is this one structure called the fovea, and the thing that we are concentrating on, the one thing we are very much interested in looking at, where spatial resolution very important, should fall on the center of the fovea. Okay. So if you're watching on a personal computer, please look at the screen on the image on top. If you're watching on a mobile phone, look at the image down, just to demonstrate the importance of the fovea. Now, when you look on the red colored image, at that time, if you concentrate, whether you can actually see the green color comb, whether you can actually really discriminate the lines, or you can get a clear vision, you will realize immediately that when you are actually vision is fixed on the red, the green is not completely clear. When it is fixed on the green, the red is not completely clear. If you really have to get a clear cut, like counting the comb, if you want to do that, okay, then you will have to actually shift focus from one to the other. What exactly is happening when you are actually looking at one and trying to determine what is happening to the next one? Why is it so blurred? The reason why the other one is blurred is just one is falling in the center of the fovea. The other image, when you are looking at one thing, is actually falling away from the center of the fovea. And that important is the fovea. You could immediately realize what is falling on what image which you are concentrating on, which is falling on the center of the fovea. You can see clearly the image that you are not concentrating on, you are not, or where it is, which is not fallen on the fovea, is not seen clearly. That important is the fovea. Okay. Now, what are the prerequisites? This is the prerequisite. Now, what threatens these prerequisites? The threat to these prerequisites, okay, are changing object of regard. You want to look at something new, which is not there on the fovea, or you are looking at something but it starts moving, that is moving object of regard. And most important in the context of today's talk is the movement of the individual. But all of these things are only a potential threat to the prerequisites, because all these threats are elegantly handled, elegantly managed by something called eye movement. Okay, there are different categories of eye movement which can take care of each of these threats. Like if the object of regard is changing, when you're looking at somebody, you're looking at the eyes, then you look at the mouth. Changing object of regard is happening, but then you are compensating that, or you are dealing with that threat actually by doing saccades. Moving object of regard, if you're watching an aeroplane, you're watching somebody walking, then the eyes engage in a movement called pursuit, and therefore that threat is taken care of, and therefore the prerequisite for vision is still maintained. And when the person himself or herself is moving, at that time also the image there is a threat that the image stability on the fovea, image being fixed on the fovea, is actually not going to be there. It may move off, but then because of eye movement called as vestibular ocular reflex, even that threat is taken care of. Okay. So when you look at this I'm going to show you. I'm holding. This is my colleague Anandu. So when you see this, what happens is I'm moving the head fast, okay, just to demonstrate what happens. And you can see that the eyes remain straight. Eyes remain straight ahead. So how is this possible? And what is this does? When the eyes remain straight ahead, it means that the eyes are able to look like when this particular head movement was being done, the eyes remain straight ahead. So what he was having as an object of regard, that continues to remain on the fovea, and therefore the person actually continues to have a very good vision. I will show that in slow motion. You can see that the eyes remain straight fixed here only. How that does is, when the head moves to one direction or the other direction, the eyes within the orbit will move in the opposite direction of head, and that you can so nicely make out in the slow motion video. So you'll be able to see when the head starts moving in one direction, the eyes within the orbits will start moving in the opposite direction. By moving in the opposite direction within the orbit, they remain stable with respect to a point on Earth. So the stability is maintained, the gaze point stability is maintained by actually moving. So you could see that within the orbit, the eyes have moved to the left, but the gaze stability is maintained straight ahead. So a movement within the orbit is needed to maintain a stable vision straight ahead, so that what was falling on his fovea continues to remain on his fovea. And this is no less function. This is a very important and a very, very essential function for us to be able to see clearly while in motion. So this is what is that. So this is how, if he was looking at the red comb, then he would have remained maintained on the red comb without actually shifting gaze. That happened because of the vestibular reflex. How does this vestibular reflex function? Just as a demonstration, in the horizontal plane, the inner ears detect the head movement, and from there the signal reaches the vestibular nucleus. Then it goes to the opposite side abducens nucleus, and from the abducens nucleus to one side abducens nerve, that is the lateral rectus, and the other side medial rectus. Both of them move the eyes in the direction opposite to the head movement, and therefore the person is still able to make sure that what he was looking at straight ahead, that continues to remain on his fovea, as we started to notice in the beginning. Okay, now this function is a test of vestibular. This is the vestibular reflex. And what are the methods that we have to test the vestibular reflex? We have the calorics, we have the rotary chair, we have the clinical head impulse test, we have the video head impulse test, we have the clinical test of dynamic visual acuity, and we also have a computerized dynamic visual acuity. So how does the clinical dynamic visual acuity do, and what are the pitfalls of that? So I'll just do one demo of how I do. Okay, this is an active mode where the person who is undergoing the test actually looks at. So there is a logmar chart here. This is a variant. This is not exactly Snellen charts. This is a little different chart. This is a logmar, which is called as a logmar chart. This is logarithm of minimum angle of resolution. And when you see, okay, I'm doing it in slow motion. Okay, just to demonstrate what happens. Now, what happens in this, the clinical test, the expectation or the ideal thing is that the person gets to look at the optotypes only when the head is moving fast, because VOR function is to stabilize eyes when the head is moving. But when you see in the clinical head impulse test, okay, as is noted so elegantly in the textbook of in the neurology of eye movements by David Z, the problem here is that the individual can get a sneak peek of the optotypes when the head has actually stopped at either end of gaze. So on that side or on this side, before the head turns around, there is a moment when the head actually stops before it actually turns around. And during that time also you get a peak. So therefore, the test may become unreliable. This is the problem with clinical dynamic visual acuity testing. Now, in this, there is a window of very, very high velocity. Okay, there is one window of very, very high velocity. What is that window of high velocity is what I want to explain. Okay, so when you see this, it starts from one place. Okay, I'm showing in a slow motion. Just see what happens. The head has come down. Then the head goes in a very high velocity. Then on the other side, it reaches zero velocity. Now with zero, it reaches a peak velocity. Again, it starts decelerating and then reaches a zero velocity. So there is one time when there is a high velocity, and the best thing that can happen for us to test, okay, is if we can somehow present this optotype in that window of high velocity and not when the head has slowed down or when the head is just begun to move, where at that time, at which time the head is very, okay, in the sense the at the time head is slow, in which case you may not be testing the vestibular ocular reflex function. We'll discuss this in even more detail in the as we go on. Okay, so stimulus has to be present in the window of high velocity. Okay, so how do we do that? Okay, this we can do with a test of dynamic visual acuity. See, when you see this, again, this is a slow motion video so that you can actually make out what happens. So I started moving to the right, I stopped. Now I start moving to the, you can see when the head does, it is not in the stopping position. It started, the optotype got presented. You will see that the optotype got presented when I was on the almost straight ahead, when I was in the almost at the peak. And then before my head slowed down, the optotype disappeared. This is two things. When does it appear and when does it disappear? It has to disappear. It has, before the head slows down, it has to appear after the head has picked up certain amount of pace. When we actually assess the performance of a dynamic visual acuity equipment, this should be the criteria. We should be able to take a 240 fps camera, stand behind the person who is undergoing this particular test, and then see whether the optotype gets presented only after the person has actually reached a certain velocity, and then does it disappear before the person slows down. This is the most important thing. If this criteria is not met, then the results of the tests are not going to be reliable. This is a very important way to measure a good dynamic visual acuity equipment. Okay, now what is presented here? Okay, what is presented here is something called a tumbling E. Okay, tumbling E in a scale called Logmar scale. What is Logmar scale? Okay, Logmar scale is a scale. Okay, Logmar scale, okay, is something called as a logarithm of minimum angle of resolution. There is more uniformity in the reduction in the size of the optotype. And what we use, okay, there are multiple things. There can be C that can be used, okay, there can be numbers that can be used, but then commonly a tumbling E is used in the dynamic visual acuity, which shows in different directions, and the person will have to identify in which direction this particular So tumbling E is very important. Okay. Now, what velocity is good enough when this has to be presented? Okay, this is a very important question that we need to answer. What velocity of the head is good enough to present this particular thing? So when you look at the mechanisms that are there to take care of the prerequisites of clear vision during movement of either the person or during movement of the object of regard, there are so many things. Okay, the optokinetic response is there. The optokinetic response itself can stabilize. Then, if there is something to where you can foveate on, there is a point you can pick up and then keep looking at it. Then, even though that point is not moving, even if you are moving the head also, the smooth pursuit mechanism can still stabilize it. That is also there. So we have slow eye movements, the optokinetic movement, the smooth pursuit eye movement. These movements are also present. So they also can take care of. So the testing should be such that it should test semicircular canal only and not other stabilizing mechanisms like optokinetic and smooth pursuit time. This is a very important criteria when you are doing. It should test the semicircular canal at its level, not the other test. So if you present the optotype at very low speeds, then there is going to be a problem. But then the other things will compensate, will take care of the vision, will take care of the stability and the acuity of vision. And therefore, what is going to happen is we are going to get a false results. Okay. then it should be able to test one semicircular canal only during a particular head rotation. Okay, that is again very important. Now, vision evoked eye movements, as I said before, the optokinetic response, these kind of things, the full field slow phase response up to 60 degrees per second. Okay, when the full field is moving, either the full field on its own or in response to head movement, is about the gain is 0.8. Okay, 0.8 is the gain. A unit gain is what can really stabilize the vision correctly. Unit gain is 1. So up to 60, it can go up to 0.8. And beyond this, it starts saturating even further, means the thing starts falling. So which means after this speed, after the eyes may still move, but they may not be good enough to take care of a clear and stable vision. Where you saw the importance of keeping something right fixed on the fovea, that function may not happen, and that is a problem. So up to 60 it may, so only after that is what, when these things start failing. So which means we cannot choose head velocities to present this in this range. So it has to be beyond this range. Is that enough? No. So when you look at the semicircular canals, there is a semicircular canal. Okay, for each semicircular canal, we know from the Ewald's law, the eye movement is in the plane of the semicircular canal. That is the first law. Then there is a second and third law which talk about the semicircular canal having a excitatory and inhibitory direction. There is one direction in which there is an excitation and the other direction in which there is an inhibition. So excitatory and inhibitory directions are there in the semicircular canals, and this is a very, very important thing to note. What is that very important thing to note is that one semicircular canal, when the head is moving, like for example, if we'll take the example of the right horizontal semicircular canal. The right horizontal semicircular canal gets excited when I move the head to the right side, and the right horizontal semicircular canal gets inhibited when I move the head in the horizontal plane to the left side. But both excitation and inhibition are neural encodings. They are neurologically valid. They can tell the eyes that the head is moving. This is very important. Both are valid neural encoding mechanisms. So which means the right horizontal semicircular canal, just for example, I'm taking one canal, can detect both the rightward and the leftward movement. But where does the difference arrive? Look at the neural response in terms of spikes per second. So there is somewhere around 70 spikes per second resting discharge rate for this particular studied semicircular canal. Okay, this is from the Vestibular System, A Sixth Sense by Goldberg et al. It's a very beautiful book which talks about all the basic sciences in the vestibular system. Okay, it's a red book. It's a wonderful book. It is one book that people who are interested in going into the basics. Okay, not exactly clinical book. It's a basic sciences book for the vestibular system. So here there is the baseline firing rate of around 70. When the head is moving in the excitatory direction, they go up, and when it is going in the inhibitory direction, they go down. And you can, at this diagram stage only, you can make out that this side the response is more, and on the other side the response is not that much. So you can see an asymmetry in the response versus excitatory versus the inhibitory direction. But what is the minimal level at which this asymmetry in response starts becoming important is what we need to study. So for that, what we do, okay, this baseline of 70, we will keep it as re-render it mathematically as 0, and then we will see how things will happen in another chart. Okay, this again is a book, is from the same book. So when you see at 32 here, triangles are there. At 32 degrees per second peak velocity, that kind of a peak velocity sinusoidal motion, when you do, there is almost a symmetric response both towards the excitatory and inhibitory direction. This 0 is a re-rendered 0. There can never be a negative spikes per second. This is in reference to previous year. This 70 becomes 0, and then above that is considered as all positive. Below that is considered negative. Okay, so okay, that is why you can see that it never goes below the 70 here. Okay, so what you see here is at 32, the response is very symmetric, which means if you move the head at that speed, then the right canal or the left canal, either canal, if one are good enough to run the eye. So you are not specifically if you're not specifically engaging one canal for that particular eye movement. It's only after that, okay, like at 64, a small asymmetry starts developing, and 128, it becomes even more, and 256, even more. So at the minimum of 64, you can start seeing the asymmetry in the response, and beyond that, the asymmetry in response goes on increasing. So these are two things. That is why it should always be beyond these levels. You should not engage the canal that is not being tested. One. Two is you should not engage the, or the head velocity should be beyond the stabilizing capability of the slow eye movements. Those are the optokinetic pursuit eye movements. Okay. So now, so this is the velocity. So that is why around 100 velocity, okay, with 20 this side and 20 that side is chosen to do the dynamic visual acuity at the first level, dynamic visual acuity at the first level. Then there is, beyond that, we can go on increasing the dynamic visual acuity at multiple levels like 150, 200, 250, 300, and 350, up to 350 also, the vestibular ocular reflex can stabilize vision. So there is a first level of testing that we can do, and then we need to go on increasing the velocities and do the test. Okay. So now this is the principle. So you are testing one canal and you are testing only the canal. You are not testing other slow eye movements. This is a key finding, key thing to be kept in mind when we are doing the dynamic visual acuity. Now, what can computerized dynamic visual acuity diagnose? The loss of function in the semicircular canals. Okay, there is no evidence. Okay, there are published literature which says like the loss of function in the superior canal after plugging for dehiscence. Okay, superior canal dehiscence syndrome. Okay, we can show with dynamic visual acuity that that canal, if it is not functioning, that asymmetry becomes manifest when you're testing that particular plane. Then there is the unilateral vestibulopathy. One example I've taken is vestibular neuritis. Then there are multiple other types of unilateral vestibulopathy. This vestibular neuritis is something that comes and stays for many days. Then there are other varieties where there is a unilateral loss of vestibular function temporarily for some time, like in mini erase disease. There may be loss of vestibular function for a few for minutes to hours, and then after that it comes back. So you can do that during the acute phase. You can do the testing. Even after multiple attacks of mini erase disease, probably that then what will happen is that inner ear gets damaged, and that also can lead to loss. Then bilateral vestibulopathy. One example is autoimmune as a result of autoimmune disease of the inner ears. Then it can also happen. Okay, in some people, okay, age-related vestibulopathy. Then there are people in whom bilateral vestibulopathy used to happen as a result of drugs. So any of these causes bilateral vestibulopathy, you can. It is not. These are not just indicative diagnosis. Any cause. Okay, it could be a tumor, whatever, which causes loss of function in that particular canal. You will be able to pick up that. Then the other thing here is visually non-stabilizing viewer. The viewer gain can be there, can be normal. I mean, can be present. Like when the head moves in one direction, the eye may continue to move in the opposite direction, but it may not be a stabilizing viewer gain. There may be extra gain, or there may be a little shortfall. So in which case, the eye will not remain, the object of interest will not remain on the fovea, which means the person will not be able to see well. So the viewer gains may be within normal limits as assessed through other means, but then the patient may still be having suffering. Like I can't see when I move my head fast, but then other tests are showing everything to be normal or within the normal range. So whether you are really able to continue to foveate the object of interest or not, is it a visually stabilizing gain or not, you can test by doing the test, this thing. Then any lesion in the VOR pathway, it can be multiple sclerosis, any other pathway, because it is not just the test of that particular end. Any problem with through the entire VOR pathway. In the beginning, we saw a diagram of vestibular ocular reflex pathway. It only begins. The afferent loop only starts in the semicircular canal, but then there is a center and there is a efferent loop. So any problem anywhere, okay, it will show up. Then we can differentiate compensated from uncompensated vestibular loss. This is a very beautiful thing that I want to take some time explaining. So if you're okay, my video can be optimized or increased so that people can actually look at me now. Okay. So to differentiate compensated from uncompensated, this is a very important thing. So here I want to introduce a concept called efference copy. Okay, what is an efference copy? Okay, efference copy is something that comes like when I start thinking about moving my head from left to the right side. That is a decision that is taken at the cortical level, and then through the motor pathways, I am implementing that decision and my head moves. This particular movement that my head is going to move at certain velocity at this particular time is also going to be, that information also can be sent down to other systems. Okay, this is the beauty. And what is the sensory consequence of a motor action? What is the expected sensory consequence of a motor action? Can also be fed downstream at, okay, what all these volitional movements can be fed downstream to other sensory systems. This or other motor systems. This is a very, very important thing. This is the efference copy. And this efference copy plays a very good role or very important role in some types of compensation. So what happens is when I'm moving my head, I send the signal down that I'm not just moving, I'm moving my head, I'm going to move it at certain velocity. Therefore, the eyes can begin to move in the opposite direction at a certain. So now that's stable. So how do we unmask the difference between the two things? In the dynamic visual acuity testing, we can have a passive mode and we can have a active mode. The passive mode versus the active mode is such that when you are using the passive mode, okay, the test is, we're going to demonstrate, okay, the test later on. So you can do the test where the person is not able to predict when that movement is going to happen and predict which direction the movement is going to happen, and then you do the test. Whereas in an active mode, the person himself or herself does the head movement. When the person herself or himself does the head movement, at that particular, in that, an efference copy can be engaged. And if you see a significant difference between active and passive, you can consider that that person has tried to compensate for the loss by engaging the efference copy. So that way you can know that this person is now, whereas in the passive, the person is not able to get, she or he is not able to get the correct scores, okay, with passive test, whereas in the active test, they are able to do that. This is a very important differentiation. Now, the other question, I have a V-hit, do I need a DVA? See, V-hit is a very beautiful test, a test of vestibular ocular reflex function. And it is like, for many practical purposes, it is considered the gold standard. Now, the most V-hits that are there presently use only one eye, okay, to measure the response, the VOR response. And even if they are measured, the two eyes also, the exact teaming of the two eyes, how exactly, it's very, very difficult to measure. Whereas you can get the gain value, you can get, but are they really teaming together or not? Or is there a small amount of disconjugacy that is developing when the head is actually moving the two eyes? Maybe a small amount of disconjugacy between the right and the left eye. If they don't move together enough, then during head movement, the VOR may look normal as measured, but the person may tell, when I'm moving the head, I cannot see clearly, though measured responses are normal. So the teaming of the eyes, if they're really happening, then you should be able to discriminate the small optotype. If you're doing that, that means eye teaming is working well. Then, so is the response visually, functionally stabilizing for the gaze? We may get, like when you see, okay, pointing to 1.1 or something like that is a good enough gain as a measure, but is it really stabilizing, or is it just overshooting, or is it just undershooting a little bit? What better than being actually foveating something to be able to discriminate a small optotype? What better test we want to best be sure that it is actually functionally stabilizing? Okay, that is one thing. Now, what else can I do? We can monitor the progress of rehabilitation. Okay, when you do rehabilitation for patients, and there are studies where DVA has been used to tell the patients this much you have improved, this much you have not improved, and this is the result of your continuing doing your exercises. Now you got this amount of result, you want better result, you continue, something like that. So it can help in monitoring the progress and which of your rehabilitation maneuvers are really helping, which of our maneuvers are not helping this particular patient. So these things can be deduced. So monitor the progress of our rehabilitation maneuvers. Then another beautiful thing is concussive injuries, mild traumatic head injury. Okay, for these things, okay, where no other disability can probably be elicited, these are things where you can use the dynamic visual acuity to screen for concussion, to screen for minor traumatic head injury. And there are people who are finding applications for this in psychiatry, in psychology, okay, so cognitive sciences, so many other things, but then I'm speaking here more vestibular and a little about mild traumatic head injury is what I made a note here. Okay. What's happening? Now, what are the steps of the DVA? So, in the steps of the DVA, the first and foremost step is determine the baseline visual acuity. How good is the person's vision, the acuity of vision? Vision has multiple things: acuity, color vision, field of vision. Okay, so many things we test. Okay, now what is the baseline visual acuity? So, if the person sits in one place, different optotypes are presented to the person, and then we find what is the baseline visual acuity. Then we get whether it is 0.1 log mark, 0.0 log mark, minus 0.1 log mark, 0.3 log mark, whatever is the baseline visual acuity for that particular person. Okay, it doesn't matter how much is it. Okay, because what we are trying to test is VOR function, and therefore, how much ever is the baseline is, it is only going to work as a reference for us to interpret the tests of dynamic visual acuity, and it is not going to be of any value to us otherwise. So we just need to know the baseline visual acuity. Then we do a test called stimulus presentation time. Here, what happens is, when I was showing the slow motion videos, I was showing something, okay, that there is a window of high velocity which we get. That window of high velocity is a very short duration window. Okay, if in big arcs, we may get it for 40 to 60 milliseconds. That's all. So the person should be able to discriminate something which is presented for a very short flash of time. Does the person have that cognitive ability to pick up something that, okay, to recognize an optotype that just shows like this and then goes off? So for that, what we do, we start presenting a different type for different lengths of duration. You start with 160 milliseconds, then 140, 120 milliseconds. A second is 1000 milliseconds. So when you're talking about 160 milliseconds, like 1/5 of a second, then it comes down, okay, less than 1/5 of a second, then it comes down. Then at 20 milliseconds intervals, it keeps coming down, and then finally we reach up to 20 milliseconds. So 20 milliseconds is like it just comes and goes, and at that time, whether the person can actually discriminate or not. When a person reaches 40 or below, that means this person's dynamic visual acuity test is reliable. The results are going to be reliable because this person needs a stimulus presentation which can be presented within that high velocity window. The key here is the high velocity window that we get, not when the head has stopped, not when the head is moving, not when the head has stopped or just making a turn where it is very close to zero, but when the head has reached a certain velocity and then it has to disappear before the head slows down. That is very important. And so that small window, whether this you can present or not, you will determine by testing this stimulus presentation time. Then post which we will do dynamic visual acuity testing. Here we have horizontal canals, right, left. Then we can test the canals in the LARP plane and the RALP plane. And then if you are for some other indications, then you can simply do horizontal and vertical. So either ways. If you want to go specific to the canals, you can choose the canal planes. And here also, again, the equipment is very important. Equipment should not be depending on a mathematically derived canal plane stimulation values. It should be getting it directly. It should be using sensors which can actually detect it in that particular plane, and that is what is going to make this the system reliable. Okay, if you place like a generic sensor in any plane and then get mathematically derived values in the canal plane, then it may not be reliable. So it has to be directly measured in the canal plane. That is very, very important for LARP and RALP. Then the gaze stabilization test is the final one. See, dynamic visual acuity is tested around 100 degrees per second peak velocity, but gaze stabilization test takes you to the maximum that VOR can support. Okay, and this is very important in certain sports individuals and these things. Okay, and where you suspect probably the lower range in a particular canal as a as a compensation or whatever has actually improved. There's a resetting of the baseline. Okay, the background stimulation rate, which will make one canal better for both right and left. If something like that is happening, you will need to engage the canal in a much higher velocity. So for that, we have gaze stabilization. It can go up to 350 degrees per second at steps of 50 degrees per second of peak head velocity. Therefore, you can do that in any plane. Okay, so this is the different kinds of steps. And okay, now interpretation of this test, how much is good, how much is bad. Okay, as we go on using this equipment, as we go on and testing more patients, okay, we will gain even much more as a community, all of us together, we will all gain, and then we will all start adding, and this is subject to improvement further, whatever. But with the normatives that we have collected so far, loss of 1 logmer is normal, loss of 2 logmer, interpret it with caution, loss of 3 lines, it indicates VOR function. Okay, this is the thing that at this point of time, with the amount of normatives that we have collected, this is the interpretation, and this is largely corroborates with the dynamic visual acuity literature that is available. The literature that is available also alters because of the different types of charts that are used, the different types of measuring that they have done. Not many actually measure the head velocity. They derive the head velocity by actually calculating the angle of head movement and the frequency of head movement. So that different kinds of tests are there, different kinds of literature is available. Therefore, there is some amount of this thing. So, but then this is with the normatives that we have collected so far. Okay. Now, this particular dynamic visual acuity device that is going to be unveiled in some time in front of you, this has happened because of a lot of effort. Okay, there are so many people, okay, involved in making this come to fruit. Okay, so these are some of the people whom I want to mention by name. Okay, we have Ajit here, who is the main chief software architect, who's done the work when it comes to building this software, the interaction with the hardware, okay, the kinds of optotypes that are supposed to be presented, the algorithms, okay, the functionality where you saw when exactly it is presented, these kind of things. We have Sudarshan, okay, who's the person who has designed the hardware, the looks, okay, the feel, make sure that the electronics talk well, okay, with the computer, okay, this kind of, and then sourcing things, okay, from godowns, okay, different, this is a pandemic time, okay, we don't know who knows where what is available. This is the kind of, okay, stupendous work that he has done. Then Malini is there. She's built the firmware, okay, which is like this is a firmware which needs sampling at very, very high frequencies. Okay, this is like aircraft level sampling, which is needed, and that kind of firmware is very important. And then I have my good friend Anand, who has developed the board for us, and I'm so proud of this one achievement, that this board is a completely made in India electronics board. And to come up with a made in India electronics board during this pandemic time, when there are chip shortages across, when there are semiconductor industries are going through, there are a lot of challenges. Okay. So we come up with a design, and the design is completely working beautiful. One part semiconductor component, one processor is just goes out of stock. And then you have to redesign using another semiconductor and then still make it work. Okay, he did that effort to make sure that it starts working. Then we have Joshi is there. So I spoke about Ajit, I spoke about Sudarshan. Okay, this is Ajit, this is Sudarshan who did the hardware. This is Malini who did the firmware. This is Anand who did the electronics. Okay, and this is Joshi, who helped in the beginning with a lot of with the software part. Okay, then Mayur. Okay, we do something called as a monkey testing. It's a thing called, which means we just don't give regard to how a device is supposed to be used. We start using it in multiple different ways to find out flaws. So he is like an expert in that. He does all the testing, comes up with all kinds of different kinds of places where, oh, this is not working well, this is showing up this error, that kind of continuous thing that happens to do that. Then we have okay, Deepthi is there, and Pramod is there. So Pramod is our expert when it comes to the regulatory aspect. He makes sure that what are all the emission requirements, safety requirements. He fetches books from all IEC standards, everything. This has to meet this particular standard. Okay, so that this has to pass. Okay, whether it is a CE or whatever. So if it has to meet that standard, this is what it is supposed to be inside. He tells us, he makes sure that those things are met. Then here Deepthi, okay, to a great extent, she has done the UI part. Under each command, there is a functionality. Under each button, there is a function. See, make sure that each of those functions really work well, really work as they are intended. This particular team, and this during this pandemic time, there were a lot of problems. There are a lot of problems to different, like each and every step we take. Okay, there are times when we needed to take a step, 2 steps backward and back forth, and it was hugely challenging. But then ultimately, they have delivered this. This tech team has delivered this to us. Okay, this is 4.5 years ago. We launched the BalanceEye, and that was the first product. And today we have another major product. We have other products in between, and today we have another major product that is launching. This was the first thing that happened in Calcutta. That was in 2017 February. That was our proud moment. And at this particular point in time, I had told on the stage, the beauty of this particular system that was launched is, other than me and Niranjan, all other people in the team were sub 30, less than 30 years old. And that is what less than 30 years old could give to this world, with encouragement, with opportunity, with some absorption of failures. Okay, that is what, if companies can take care of that, then we can do it. And today they have done the next big thing. Okay. And I once again thank you all. Okay, I thank you all for being part of this, for taking. I know evening is a very, very busy time, but then you thought it, okay, you deemed it important to log in, to say that you are with us, and that means a lot. Thank you all.
Okay, so let's move on with the main event for the day, which is basically unboxing of BalanceEye DVA by Dr. Deepak Haldipur, who's a senior ENT consultant, and he's been a well-wisher of Cyclops right from day one we started. And he's been kind of hand-holding us and helping us navigate, understand and navigate the entire clinical ecosystem, especially in the ENT domain. And he's also director of Trustwell Hospital. So today he's there with us to unbox the product. May I request Deepak sir to turn on the video?
Yeah. Hi Niranjan, and hi VR and the team of Cyclops and the delegates who have logged in. It gives me immense pleasure to be here to unveil or release the BalanceEye DVA, which is the next kind of a release from the Cyclops. As you all know, that the Dynamic Visual Acuity has its own advantages, especially in vestibular lesions, where we have to differentiate the peripheral and central, and unilateral and bilateral vestibular lesions, like you see vestibular neuritis, Meniere's disease, diabetic vestibulopathy, labyrinthitis, specifically the lesions concerning the superior semicircular canal, the lateral or the horizontal semicircular canal, and the posterior canal as well. So this was to be coming as a natural progression with the intense passion that Srinivas and the sustenance and the consistency of Niranjan And I know these guys from the day I started. It's one of the startups that I'm very, very confident about because they're on firm grounds and they're doing something. And I'm sure all of you have already been using their VNG machine, the BalanceEye, would be very happy to now add on this Balance DVA to their repertoire. Without wasting much of your time, let me unveil or release the BalanceEye, which you can see now. And this is here for you guys to see very much. And this is unveiled here. I think a big round of applause for the a big round of applause for the BalanceEye people, especially Cyclops. I know the amount of effort you guys would have put in for this. And I know just like your BNG and other products, this is also a clear winner. I can see that. And for people who are practicing vertigo and the postgraduates of BNP, let me tell you, vertigo is becoming a bigger clinical problem that we are facing, especially in the last 10 years. I can see a huge march in the number of cases, and even at Trustwell, the early ENT group, we find that vertigo forms a big chunk of our practice. And thanks to the BalanceEye VNG, and now of course BalanceEye Dynamic Visual Acuity DVA, I'm sure that I'll have more number of happy clients going out from my clinic who come to me with vertigo with more accurate diagnosis, proper treatment, and in-point rehabilitation. Thank you so much for involving me in this. It gives me a matter of pride. It also goes with our Prime Minister's vision that this is a genuine, world-class Make in India product. Hats off to everybody and all the best to everyone who is involved in the project, especially DR, as we call him, our dear DR Srinivas or Srinivas Dorsala, and Niranjan Sukha. All the best.
Thank you, sir.
Thank you so much, sir. It was indeed a great pleasure that you consented to come on a busy OPD day to do this honors for us. We are greatly indebted to you. And so with this now, let's move on to the next bit of the program. So before we move on to the demo, right, there is, see, like Srinivas explained earlier, right, we have a great team out here who have put in a lot of effort during the pandemic time to build this product, right? So today we have pulled two of our team members to share their excitement on what went into building this and what, according to them, are some of the unique aspects of this. So they'll probably take a minute to share their excitement. And after that, we'll have a quick demo of the product by Anantu. So I would request Sudarshan and Ajit to come over and share a couple of words.
Thanks for giving a chance to share a few lines. Yes, first of all, I would like to say this is one of that product we can say conceptually simplicity with technical complexity. Why I'm saying because this product deals with both hardware and the software with the highest precision and functionality. Merging both for the best result is a laborious job in the research and development. Even in the middle of the pandemic and the global semiconductor crisis, we are successfully able to manage to overcome this hurdle to deliver the product. And so far, the product undergone a very vigorous testing and trial in the Cyclops. And now today is the official day. We are going out of Cyclops where it's designed to belong. And I'm very excited to see the intended usage in our customers' hand. And finally, thanks for the close guidance of Dr. Srinivas to develop this product. And I'm very glad to work with the eminent team of Cyclops. Thank you.
Hi, good evening, everyone. I am Ajit. I am a software architect at Cyclops. So, since Dr. Srinivas already explained about the application of the DVA, and in another 5 minutes, we have a detailed demo of the product. I would like to use this opportunity to thank our team members who have put enormous effort in bringing this product. Though it looks a very simple product, the lot of effort has gone into building this simple product. So basically, I would like to highlight two aspects of this product. One is when we decided to make this product, the first day itself, Dr. Srinivas told, if this product can deliver the intended use, then only it makes sense. Like if we can get the head velocity and the other sensor details at the right time, then only we can tell it as a complete product. Otherwise, it is not a complete product. So we had this thing in mind. And secondly, we intended to make a very useful, straightforward user interface. So a lot of effort has gone into making this product as a very simple and user-friendly product. So with this, we believe this product can be a very handy tool in diagnosing patients quickly and accurately. So first of all, I would like to thank Dr. Srinivas for his guidance, because he has involved in every stage of the product development, whether it is a hardware, software, firmware, anything. So he involved from the day one, and he has contributed in every aspect of the product development. So big thanks to him. And of course, Niranjan and our team continuously supported in this process. So I would like to thank each and every one of them. And of course, we are very happy and excited that this product becomes a very useful tool for the doctors. And we are very happy to receive any feedback or any suggestion that makes this product further improvement. So once again, thank you each and every one of you for being part of the event. Thank you very much.
Yeah, thanks Ajit and Sudarshan. I would now request Anantu to get on with the demonstration of the product. He will do a quick show of the product, and you will probably appreciate how nimble and nifty the product is, and how easily it can be integrated into your clinical practice. It's a very small power-packed unit. And post that, he's going to quickly show you a demo of the product and also present a case study. You see, we've been using this product for a while in our clinic here. So we have already assessed quite a few patients, and of that, he's going to pick one or two case studies and present it to you here. I hope you appreciate it. Yeah, Anantu, please carry on.
Thank you, sir. So this is the BalanceEye DVA. So the product is less than 150 grams. It's a head-mounted product. So as you can see here, there are silicon stoppers over here. So if you place it over the head, there is 90% less chance for the device to slip out of that particular point. And you will see a light indication here when the device is connected. And these are the regulatory stickers which we have. And this is connected with a 5-meter long wire to the computer, like this. So we have 5-meter long wire and the head-mounted DVA. Now we will move on to the demo of the product. I'm going to share my screen now. So we have a pre-recorded video of the test, so that we have clubbed both the patient video as well as the test video together. Hope you can see my video sharing. So you have to open the BalanceEye DVA software and then enter the 3 fields. First name, age, and gender is mandatory to register and to start the testing. And then we click save button. It will take you to the main sheet of DVA. So here we have baseline visual acuity, stimulus presentation time, dynamic visual acuity, and gaze stabilization test. All the tests you will be seeing on the left hand side. And here on the right hand side, you will be seeing the head velocity. So when the head is being moved in any of the plane, it will show how much degree the head is moving. And here you can see the gyro sensor data from X, Y, and Z axis. And this is the tumbling E, the optotype which the patient will be seeing on the secondary screen. So they will see any of the 4 optotype and they have to select the particular optotype which they are seeing on the secondary screen with the help of an air mouse. So these are the optotypes. So these optotypes are mapped to the keys of the remote, the air mouse coming with the device. So if the E is opening to the right side, the patient has to press the right arrow and then press OK to give the response. If it is opening towards up, they have to press the up arrow, and for left and down, similar. So whichever image they are seeing, they have to press the arrow and then press OK button. That is very simple instruction to the patient. Now going to the baseline visual acuity. So on the right hand side, we have an image coming of the live recording of the patient. So here I have started the baseline visual acuity. You can see the secondary screen. I will be the clinician will be sitting on the side beside the patient, and patient will be given the remote and they have to select the optotype which they are seeing. So the optotype is clubbed with the sound stimuli so that the patient's attention is also towards the secondary screen when the stimulus appears. So initially Dr. Srinivas told about the optotype and the logmar scale. So we start from 1 logmar up to -3. So usually normal people will be going like 0 logmar or -1. So for every correct responses, the system will go to the next lowest point, and you can hear the beep sound also along with the optotype. The beep sound is also coming, and you can see there is a substantial reduction of the size of the optotype also on time. So now it is 0.3 logmar. Now 0.2, she couldn't make out 0.2 logmar. Yes, so 2 incorrect responses, the test will stop itself, and then now the baseline visual acuity is 0.3 here. So the baseline visual acuity is the basis of all the other testing. The stimulus which we provide on dynamic visual acuity for horizontal, vertical, LRP and RLP is based on the visual acuity of the patient. We have a stimulus presentation time also where the latency of the optotype will be different. Initially, the optotype will remain for more time. Then the stimulus, the latency will be very less. Now I'm jumping to dynamic visual acuity here for the horizontal plane. Both eyes we are testing. There are options to test only right eye or only left eye. Execution, passive means the clinician will be shaking the head from behind in all these planes. Active will be patient have to do it on their own. And now I have selected the horizontal plane here. So you can see I'm going to mount the goggle, mount the DVA onto the patient. So as I told you, it's a very lightweight product, less than 150 grams, and we have a silicon stopper which reduces the movement when we shake the head. Now I have started the, so I'm going to start the testing here. So you can see on the head velocity, you will be able to see the real-time head velocity which is being achieved when we shake the head, and you will be able to see the real-time X, Y, and Z axis movement of the gyro sensor here on the down portion. So you can see whenever I'm moving the head, so we are testing the leftward head movements first. So you can see I am shaking the head slowly towards right and going fast towards left here. So whenever there is a leftward head movement at the peak head velocity, the stimulus will be appearing on the secondary screen with a beep. So it started with 1 logmar. Now the logmar size is reducing as the test progresses. So you can see the size, the logmar which we are testing, and the head velocity, the peak head velocity at that time, and the response here. So only leftward responses are taken. Even if there is a rightward eye movement, the will not pick up, the optotype will not be appearing on the screen here. So 0.3 logmar. BVA was 0.3, so below 0.3, we'll see how the response comes. Now it is,
Yes, it is going. You go ahead.
correct. Now I'm shaking the head towards right. So whenever there is a rightward head movement, you can see the stimulus will be appearing and the responses are being recorded on the right side. Yes, like this. So basically we are exciting the right horizontal canal here and
it's
checking
coming right.
how is the visual acuity when the head is at peak velocity. We got an incorrect response here. 0.3. But the next response was correct. So the test is again continuing. Again 0.2 incorrect response. So 2 incorrect responses, the test will stop itself. Yes. Now dynamic visual acuity for the vertical plane. We are testing both the anterior and both posterior canal here, not testing it separately, specifically for anterior or right posterior. So upward and downward DV. Whenever I am making an upward movement, most likely 2 posterior canals will be excited, and we are checking the visual acuity when the head is moving upwards. You can see the head velocity graph also here on real time.
No.
0.4 log mark is
No.
0.3.
Down.
Yeah, 0.3 was the baseline visual acuity. Here also we are getting till 0.3. Now I am doing it for downward. I am exciting both the anterior canals here. Yes.
Down.
Down.
Down. Down. Right. You do up.
So again, point
One incorrect.
towards downward, we got an incorrect response. So system again, it will check 0.3. If it is coming correct, then it will move to the next lowest log mark. Now we are getting incorrect responses. Yes. Now going to the LARP, left anterior and right posterior canal DVA testing. So we are doing it passive on the LARP plane. So you can see I'm actually turning the patient's head towards right to test the right, left anterior and right posterior canal. Now I am making the head go down fast. So when I am turning the head towards right and going down, left anterior canal is getting stimulated, excited, and we are checking the response.
Right.
So when we use it for the rehabilitation, when we use it to assess the progress of the patient after vestibular rehab therapy, we can actually see the progress in the logMAR scale. They will not be performing on the lower logMAR scales in the initial stages. As the therapy progresses, as the patient will be getting a better results, that is, the patient will be responding even at lower logMAR scales, lower logMAR units. So again, the BVA, the baseline visual acuity and dynamic visual acuity
Two incorrect, now it is going to RT.
0.3. Now I am shaking, I am
Now it is
doing
RT.
the shake towards back. I am exciting the right posterior canal here by shaking the head towards back side. You can see again the test is starting from 1 degree optotype, and then the logMAR scale reduces
Right.
until the subject gives 2 incorrect responses.
Left.
So as the therapy progresses, we expect a better score in the DVA.
Down.
And in some cases, we have seen the anterior canal being spared in some cases of Meniere's. So all the other responses will be reduced other than the anterior canal. So it becomes a very good test to assess the left anterior and right anterior plane DVA and to assess the performance of the canal. Again here, she was able to do till 0.3. Now we are going to do DVA in the RALP plane, that is right anterior and left posterior canal, passive. So I'm turning the head towards left and then trying to do posterior canal stimulation here. The head is going down, eyes are moving up. Head is going up, eyes are going down here.
This voice and all.
So again, you can see it starts from 1 logMAR, then it reduces its size, 0.9, 0.8.
Left.
So we are not checking random because it becomes
Again, left.
easy if you are only checking the posterior canal first and then go to anterior canal.
Down.
Again, 0.3, subject has reached 0.3, that is a baseline visual acuity.
Do that
Right.
again.
Plus or minus 1 can be seen even in normals also. Plus or minus 0.1 degree deviation can be seen.
Right.
Here 0.1, she is not able to make out.
Right. Left. I think.
Now,
Two incorrect.
right anterior, I'm going to stimulate. I'm shaking the head towards down.
No problem.
Eyes are going up here.
Go ahead.
Down.
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 0.8.
Left. Right. Up. Left.
Now we have raised 0.4.
Down.
Yes, so we have reached till 0.3. One incorrect response, then again correct response. Yeah, 0.2. Subject is not able to make out. So two incorrect responses, test will be ended. Now the last test, that is gaze stabilization. So here I am only doing the horizontal gaze stabilization. So I'm doing it for the both eyes, passive, horizontal plane. I'm looking at the head velocity, real-time head velocity graph here for making, for shaking the head, because we require higher frequency head shake here. So I'm doing, I'm giving emphasis to leftward turning more here. So here the target velocity achieved was around 100. You can see here on the right hand side, the green line have moved little up.
Down.
So initially the target velocity was 50 to 100. Now it has become 100 to 150 and increasing
Up.
over time.
Left.
At velocity, you can see the target velocity is 250 to 300. We have achieved 266 degrees. And responses also are shown here.
Up.
So only leftward movement, as Dr. Srinivas sir presented. During the peak velocity time, the stimulus will be presented. So on the leftward turn,
This is not ready.
300 to 350 degrees, she was able to make out
This is time.
the optotype. So similar way, we are testing the rightward responses also. And when it reaches 300 to 350, the test will stop. And that is the maximum that we test. Yes. So this was a quick overview of how we do the testing. Yes.
Yeah. So thanks, Anantu, for that very detailed demonstration of the product. If anybody has any questions, please feel free to put it in the chat window on YouTube. Or else you can always send us a mail, info@cyclopsmedtech.com. We will always get back to you with answers. There are some of our audience today who's asked us how to procure BalanceEye DVA. So here are the details. If you are interested to schedule a demo, or if you would like to know more about the product, please feel free to talk to Abhishek. You have his number here. And then you may also send an email to info@cyclopsmedtech.com. We will get back to you at the earliest. We already have a bunch of our existing customers who have placed an order, and we are in the process of fulfilling that starting today. So there might be a bit of a lag, but then please do reach out and we will ensure that the product gets delivered at the earliest. So I think, yeah, and just another apology. I think we don't have the case presentation. My team just confirmed. So probably we'll put together something and share it with you at a later point of time on our YouTube channel, Cyclops Learning Lab. But I think today we don't have the case presentation. I think there's a bit of a mix-up that has happened. So I think with this, probably we are coming to the fag end of today's events. I would request Dr. Ravi Nair to close the session with his closing remarks. Yeah, I think you need to unmute, sir, and stop the share. Sir, you need to unmute. You're on mute. Ravi Nair, sir, you're on mute. You need to unmute.
Yeah, can you hear me now?
Yeah, we can hear you. Please go ahead.
Okay, so let me at the outset congratulate the Cyclops team, all of us, because I think this is a very exciting development. And I think in keeping with the philosophy of bringing cutting edge made in India technology to the vertigo space. As was beautifully presented, everybody pitched in, everybody contributed, and this is the strength of the Cyclops team. And we look forward to bringing more and more products like this with newer and newer innovative processes to make sure that Cyclops MedTech stands out as a role model for MedTech innovations in India. Thank you to the Cyclops team. Thank you to the audience. And let's hope we benefit more and more patients by this endeavor. Thank you.
Yeah, thank you, sir. Thanks everyone for being a part of this event today and share the excitement with us. So good night to everyone in India. Good afternoon and good morning to everyone elsewhere. Have a good day. Bye-bye. See you soon.